Hi, my name is Alden, and today I'll be going through optimization on scientific applications. So this lesson will look through some real-life scenario where we'll have to use optimization to solve for the problem. So learning goes, students will understand how to apply optimization on scientific problems. Students will learn how to do half-life and exponential growth and decay questions. Success criteria, students will be able to solve optimization problems related to scientific applications. So prerequisite understanding. Students should know how to apply second derivative tests to find the extrema of a function, to find the maximum or minimum. And students should also know the basic derivative rules, especially the logarithmic one. If you don't know, it's posted in the lesson notes. So feel free to go to the lessons notes and look at the rules and then come back to the video. Keywords, half-life is the time for a substance to become half of what it originally was. Exponential growth and decay, the amount of something that increases or decreases. So here are the important formulas. Feel free to write them down as we will need them along the lesson. So half-life formula, quantity remaining equals initial quantity times 1 divided 2 to the power of elapsed time divide half-life time. So 1 divided 2 is a splitting factor. Exponential growth and decay formula, final amount equals initial amount times e, which is any number, to the power of k, which is rate of increase or rate of decrease, times t, which is time between final amount and initial amount. For k, rate of increase or rate of decrease, you cannot choose both, you have to choose one. So be aware of that. So once again, these are the important formulas. Make sure to remember them. So let's go through some practice. So question 1. A certain radioactive material decays exponentially. The percent P of the material left after T years is given by the function P equals 100 times 1.2 to the power of negative T. A. Determine the half-life of the substance. B. How fast is the substance decaying at the point where the half-life is reached? So A. Determine the half-life of the substance. So half-life is basically the half of what the initial amount is. So initial amount is 100. So 100 divided 2 is 50. So we make 50 equals the equation. So the equation is 50 equals 100 times 1.2 to the power of negative t. So we can bring 100 over to the 50 side and it becomes 1 divided 2. And then we derive the right side, 1.2 to the power of negative t. We get 1 divided 1.2 to the power of t. So now we can cross multiply 1 times 1.2 to the power of t, 2 times 1. And now we can use natural log to isolate for t. So natural log, we bring the exponent t to the front and we natural log 1.2 and 2. So if both numbers that are being natural log are the same number, we can it equals to 1, so we can just remove it. But unfortunately for this case it's not, so we have to divide. So natural log of 2 divide natural log of 1.2, we put in the calculator, we get 3.8 years. So the half-life of the substance is about 3.8 years. B. How fast is the substance decaying at the point where the half-life is reached? So the problem is asking for the rate of change when t equals 3.8 years, the number we found just now. So first we derive the equation. Now for deriving this equation, we use the logarithmic rule. So it's posted in the lesson notes, as I said. So make sure if you're unfamiliar with the rule, go back and look through it. So then the equation is negative 100 times 1.2 to the power of negative t times natural log of 1.2. So now we can sub t in, 3.8 years. So we sub it in and we'll get negative 9.12. So remember, when putting this equation into the calculator, try to put the equation in one go. Don't put it in separate parts as it may mess up the calculations. So the substance is decaying at a rate of about negative 9.12% a year at the time 3.8 years where the half-life is reached. Moving on, question 2. A certain radioactive substance decays exponentially over time. The amount of a sample of the substance that remains, P, after t years is given by the function P equals 100 e negative to the power of negative 5t, where P is expressed as a percent. A. Determine the rate of change of the function. B. What's the rate of decay when 50% of the original sample has decayed? So A, for determining the rate of change, we just derive it. So we use the power rule, 100 e to the power of negative 5t. We bring the negative 5t out. and we'll get negative 5t. We derive the negative 5t, it will be negative 5. So then we can use the negative 5 times 100 is negative 500 multiply e to the power of negative 5t. So that's the rate of change of the function. B, what's the rate of decay when 50% of the original sample has decayed? So 50% of the original sample meaning the 50% of the original amount. So it'll be 50%, which is 0.5, also known as 1 divided 2 because it's the same thing. You can use both. So then the equation is 1 divided 2 equals 100 e to the power of negative 5t. So then we can bring 100 to the other side, divide both sides by 100. So it'll be 1 divided 200 equals e to the power of negative 5t. Then we use natural log. So left side is natural log of 1 divided 200, and right side is natural log of e times negative 5t. Now there's no ln e because ln e is basically 1. So 1 times negative 5t is the same thing. So you can put ln e if you want, but if not, you can just not write it. It all depends on your teacher. So then we can isolate for t, so we divide both sides by negative 5 and we get 1.06. So now we have to put 1.06 into the derived equation that we found in part A. So we substitute t for 1.06 and we get 2.5. And reminder, put this all in the calculator in one go, don't put it separate parts, as the decimals might mess up the calculation. Question 3. A rumor spreads through a population in such a way that t hours after the rumor starts, the percent of people involved in passing it on is given by the function p equals 100 times e to the power of negative t minus e to the power of negative 4t. What is the highest percent of the people involved in spreading the rumor within the first 3 hours? When does this occur? For first 3 hours, remember that the limit is 0 to 3 because 0 is the start of when the rumor started spreading, and 3 hours is the limit they want. So anything above the hour 3, so like 4 hours, we don't use that. So first we find the critical numbers. To do that, we have to derive the equation first. So we use the derivative rule. So we get 100 e to the power of negative t times 1 plus 4 e to the power of negative 3t. So then we find the critical numbers, we make it equals to 0. So 4e negative 3t equals 1. Then we divide both sides by 4. Then we can use the natural log. So natural log of e, which is 1. So then left side will just be negative 3t equals natural log of 1 divided 4. Then we can divide t. We can divide both sides with negative 3, so we can isolate for t. So t, it will be negative ln times 1 divided 4 divided 3. So then we put it into the calculator and we get 0.462. So this critical number 0.462 meets the requirement of the limit 0 to 3. So the number has to be bigger than 0 but also less than 3. So it meets that requirement. So we can use it. We plug it back to the original equation. We plug all the values we got, even the intervals. So the function p with the value 0 equals 0. The function with the value 0.462 equals 47.2, and the value of 3 into the function equals 4.98. So we can see based on here that the highest percentage of people spreading a rumor is 47.2% and occurs at the 0.462 hour point. So that is the end of the lesson. Make sure to do the homework, and if you are completed with the homework, you can do the assessment. And yeah, thank you.